The architecture wasn't supposed to leave the building. That's the strange part. For years, Nvidia's dominance wasn't just about manufacturing power or software ecosystems. Plenty of companies had access to advanced fabrication. Plenty of firms could hire brilliant engineers. What separated Nvidia was something much harder to copy: the internal logic architecture that determined how billions of transistors communicated, prioritized tasks, and moved data through increasingly complex workloads. And yet, according to emerging reports from Chinese defense and semiconductor circles, a military-oriented accelerator system built around a remarkably similar logic gate philosophy has now entered deployment. Not a laboratory demonstration, not a university paper. Deployment. The sanctions were designed to prevent exactly this outcome. That fact alone deserves attention, because if the reports are accurate, then the conversation around China's semiconductor industry has been missing something important. The debate has focused almost entirely on manufacturing nodes: 7 nanometers, 5 nanometers, EUV lithography, ASML machines, export controls. Those things matter. They matter a lot. But there is another layer. A chip is not valuable because it contains billions of transistors. A chip becomes valuable because of how those transistors are organized. Think about it this way. Give two architects the same amount of steel and concrete, and one builds a warehouse while the other builds a skyscraper. The materials are identical. The design isn't. The same principle applies to advanced computing, which brings us to the question almost nobody was asking a few years ago. What happens if China stops chasing manufacturing leadership and starts focusing on architectural innovation instead? That possibility looked remote in 2022, when Washington launched its most aggressive semiconductor restrictions in decades. The objective was straightforward: limit access to advanced GPUs, restrict high-end manufacturing tools, slow military AI development, extend America's technological lead. The logic seemed sound. Many analysts assumed China's most advanced military AI programs would face serious bottlenecks within a few years. Yet something unusual happened. Chinese institutions didn't stop building. They changed direction. Funding began flowing toward alternative accelerator designs. Universities expanded research into specialized computing architectures. State-backed entities started treating logic efficiency as a strategic priority, rather than merely pursuing smaller process nodes. The result wasn't immediate. Nothing about semiconductor development is immediate. But 3 years later, the picture looks different than many expected. A growing number of Chinese defense-related systems appear to be achieving surprisingly competitive performance, despite operating under constraints that were supposed to cripple them. Notice the word competitive. Not superior, not dominant. Competitive. There's an important difference. Some commentators jump from every Chinese breakthrough directly to declarations that America has already lost the technology race. I don't buy that argument. Nvidia still possesses enormous advantages in software, ecosystem integration, developer adoption, and cutting-edge design experience. Those advantages are real. But dismissing what China has accomplished would be equally foolish. Because the most interesting development isn't that China built another chip. It's that Chinese engineers seem to have identified a different route toward performance. And if that's true, then the implications extend far beyond military hardware. Remember that phrase, different route. We're going to come back to it repeatedly. Because hidden inside this story is a much bigger question about technological competition itself. What if the race was never about building the smallest transistor? What if it was about discovering smarter ways to connect them? That distinction may explain why some Chinese military systems are attracting attention from analysts who previously ignored them entirely. And the trail leading to that conclusion begins with a decision Nvidia made years ago, one that looked like an engineering choice at the time, but increasingly resembles a strategic asset. The decision looked boring when Nvidia made it. Most breakthrough technologies look boring at first. Engineers weren't standing on stages announcing a revolution. Investors weren't celebrating it on earnings calls. It was buried inside technical design choices about data movement, instruction scheduling, parallel execution, and the arrangement of logic pathways that determined how information flowed through increasingly dense computing systems. Yet those decisions became part of the foundation of Nvidia's rise. To understand why, we need to separate two concepts that often get mixed together. Computing power and computing efficiency are not the same thing. Adding more transistors can increase power. Organizing them intelligently increases efficiency. For years, Nvidia became exceptionally good at the second category. Its engineers understood something that many competitors underestimated. Modern AI workloads spend enormous amounts of time moving data rather than actually performing calculations. That sounds absurd until you think about it. Imagine a factory where workers spend half their shift walking between machines instead of building products. The problem isn't worker capability. The problem is factory layout. Advanced processors face a similar challenge. A surprising amount of performance comes from reducing computational traffic jams. This is where architectural design becomes a strategic weapon. One reason Nvidia maintained such a commanding lead was that its products weren't merely faster. They wasted less effort, less waiting, less unnecessary movement, less energy spent moving information from one location to another. That advantage compounded over time. Now here's where things become interesting. Chinese researchers studying AI accelerators throughout the late 2000s weren't just examining manufacturing techniques. They were publishing papers on interconnect structures, memory hierarchy optimization, workload-specific logic allocation, and adaptive processing pathways. Most of those papers attracted almost no attention outside specialist circles. They weren't exciting headlines. Nobody clicks on a news article titled, "Novel Data Flow Optimization Framework for Parallel Processing Environments." Meanwhile, newspapers focused on export controls, governments focused on sanctions, investors focused on quarterly earnings. Chinese research groups focused on architecture. Different priorities produce different outcomes. One underappreciated example emerged through collaborations involving institutions connected to the Chinese Academy of Sciences and several defense-affiliated research centers. Rather than attempting to directly replicate Western GPU designs, researchers increasingly explored domain-specific accelerators optimized for particular military tasks. Target recognition, electronic warfare, signal analysis, autonomous decision support. Instead of building one processor for everything, they investigated processors specialized for certain jobs. There's a reason nature does something similar. The human brain doesn't use identical structures for every function. Different regions evolved for different tasks because specialization often beats universality. Military AI systems benefit from the same principle. And that's where the Nvidia architecture discussion can become misleading. I don't think Chinese engineers copied Nvidia in a simplistic sense. The evidence points somewhere more interesting. They appear to have studied why Nvidia's architectural choices worked, extracted underlying principles, and adapted those principles to different objectives. That's a much harder achievement. Copying a blueprint is one thing. Understanding the logic behind the blueprint is another. There's a reason countries spend decades trying to acquire technological know-how rather than merely purchasing hardware. Knowledge scales. Hardware depreciates. A small example illustrates the difference. When the United States restricted exports of advanced AI accelerators, such as the A100 and H100 series, many observers assumed Chinese military computing progress would stall dramatically. Reasonable assumption. After all, those chips represented years of engineering effort, yet several Chinese programs continued moving forward through combinations of domestic accelerators, architectural optimization, software adaptation, and distributed computing approaches. Performance suffered in some areas, but development didn't stop. The prediction and the reality diverged. That should make us curious, not alarmed. Curious. Because curiosity is usually more useful than certainty when technology is evolving this quickly. There was even a moment of unintended comedy buried inside the situation. Washington restricted access to some of the world's most advanced AI processors. Chinese engineers responded by spending more time figuring out how to use less hardware more effectively. That's not the outcome policymakers were hoping for. Still, an important counter-argument deserves attention. Even the most elegant architecture cannot completely compensate for manufacturing disadvantages forever. Physics remains stubborn. Smaller nodes generally provide advantages in power efficiency, transistor density, and thermal performance. The laws of semiconductor engineering have not been repealed. China knows this. American companies know this. Everyone involved knows this. Which raises an uncomfortable strategic question. What if architecture and manufacturing aren't competing explanations? What if they're multiplying each other? Because if a country eventually improves both at the same time, the competitive landscape changes dramatically. And that possibility brings us to a little-known military project whose significance has less to do with the hardware itself and more to do with what its existence suggests. Remember the phrase from earlier, different route. We're about to see where that route leads. A military technology story usually begins with a weapon. This one begins with a bottleneck. Around the world, defense planners are confronting the same problem. Modern military systems generate absurd amounts of information. Satellites collect imagery. Radar networks scan continuously. Electronic intelligence platforms intercept signals. Autonomous systems stream sensor data every second. The challenge is no longer acquiring information. The challenge is deciding what matters before the opportunity disappears. A missile traveling at hypersonic speeds doesn't wait for a committee meeting. That reality is driving a new generation of military AI infrastructure, and it's where China's reported deployment becomes significant. Because the value of these systems isn't measured by benchmark scores. It's measured by decision speed. Imagine two commanders receiving identical streams of battlefield data. One system identifies threats, prioritizes targets, filters noise, and recommends responses in 3 seconds. The other requires 15. Both systems technically work. Only one survives the future battlefield. This is why defense organizations increasingly care about architecture-level efficiency rather than raw computational bragging rights. And here's the reversal that changes how many people view this story. The most important question may not be whether China's military processors are equal to Nvidia's best products. The more relevant question is whether they are good enough for the missions they're designed to perform. Those are completely different standards. A lot of Western analysis quietly assumes technological competition resembles consumer electronics. Fastest processor wins. Highest benchmark wins. Largest performance number wins. Military organizations don't always think that way. Reliability matters. Cost matters. Availability matters. Domestic production matters. A processor that is 20% slower but can be manufactured, maintained, and deployed without foreign approval may be strategically preferable. That doesn't make it superior technology. It makes it useful technology. And usefulness often beats elegance in military planning. Let's zoom in on one example. Several Chinese defense-related research programs have focused heavily on intelligent sensor fusion. That's the process of combining data from multiple sources, radar, infrared systems, satellites, electronic surveillance platforms, into a coherent operational picture. Sounds straightforward. It isn't. Different sensors generate different formats, different refresh rates, different confidence levels, and often contradictory information. An AI accelerator optimized specifically for these workloads doesn't need to outperform every Nvidia product on Earth. It only needs to process relevant information faster than the opposing system. That distinction matters enormously. Remember the different route we've been tracking? This is it. Instead of attempting to dominate every category simultaneously, Chinese military computing efforts appear increasingly focused on narrowing performance gaps in strategically important areas. That approach has historical precedent. Japan followed versions of this strategy in advanced manufacturing. South Korea used elements of it in memory semiconductors. Even the United States benefited from targeted specialization during several periods of technological competition. Nobody wins every sector at once. The successful players identify leverage points. Which brings us back to the architecture itself. The reports attracting attention aren't suggesting China discovered some magical new law of physics. Nothing that dramatic. What's attracting analysts is evidence that Chinese developers may have become significantly better at extracting performance from constrained resources. And if true, that creates a very different strategic equation than the one many expected in 2022. Because sanctions generally assume constraints create delays. What happens if constraints create adaptation instead? Not always, not automatically, but sometimes. History offers uncomfortable examples. American restrictions on Japanese technology during the 1980s encouraged domestic innovation in several sectors. Soviet space achievements emerged despite substantial economic limitations. Even early Silicon Valley companies often developed breakthrough designs because resources were scarce rather than abundant. Pressure can break systems. Occasionally, it hardens them. I'm not claiming that's definitively what happened here. The evidence remains incomplete. Many details surrounding these military deployments are naturally classified, and some public reporting almost certainly exaggerates capabilities. Skepticism is healthy, yet the broad pattern deserves attention. China's semiconductor story increasingly looks less like a race to copy the West and more like an effort to build alternative pathways around Western advantages. That's a different challenge entirely, because competing against imitation is one thing, competing against adaptation is another. And this leads directly to the bigger question hanging over the entire technology competition, a question that matters far beyond military hardware. What if the most valuable thing Nvidia accidentally demonstrated wasn't a specific architecture at all? What if it was a method of thinking about architecture? Because if that's the lesson competitors learned, the consequences won't stop at China's military sector. They'll spread into the next generation of global computing itself. The story started with logic gates. It ends with assumptions. For much of the past decade, the dominant assumption in Washington, Silicon Valley, and many policy circles was that semiconductor leadership could be measured primarily through access to the most advanced manufacturing technology. There was good reason to think that. Companies such as Nvidia, TSMC, and ASML built advantages that were extraordinarily difficult to replicate. Entire ecosystems formed around those advantages. Supply chains stretched across continents. Talent accumulated in specific regions. Expertise became concentrated. None of that disappeared. Anyone predicting the collapse of Western semiconductor leadership is getting ahead of the evidence. But something else happened alongside that dominance. Competitors started learning. And learning is harder to sanction than hardware. That's the thread running through this entire story. The architecture that Nvidia spent years refining wasn't valuable simply because it existed. It was valuable because it demonstrated a way of solving computational problems. Once engineers understand the reasoning behind a solution, they begin creating their own versions. Not identical versions, adapted versions. Sometimes inferior, occasionally better suited for a specific purpose. The military deployment reports coming out of China matter because they suggest this learning process has progressed further than many expected. Again, that's not the same thing as technological supremacy. Let's keep our feet on the ground. China still faces major challenges in advanced lithography, manufacturing equipment, software ecosystems, and several areas of semiconductor tooling. Those obstacles are real. The gap hasn't vanished. But the narrative that restrictions would simply freeze Chinese progress appears increasingly difficult to defend. What we're seeing instead is a long-term adaptation cycle. And adaptation has a habit of surprising people. Remember the question from the opening? What if the race was never about building the smallest transistor? The answer is that transistor size still matters enormously. But it's no longer sufficient as a standalone measure of capability. Architecture matters. Software matters. Integration matters. System-level efficiency matters. Military usefulness matters. The future belongs to whoever combines those elements most effectively. That realization changes how I look at this entire situation. A few years ago, many observers treated Chinese semiconductor development as a manufacturing story. Today, it increasingly resembles an engineering story. That's a subtle shift. Yet subtle shifts are often the ones that reshape industries. My own view is fairly simple. I don't think China has secretly overtaken Nvidia. I don't think American technological leadership is about to disappear. I also don't think the existing gap will remain as large as many people assume. The data points toward a more competitive future than either side likes to admit. And competition creates consequences. For governments, it means export controls become less effective over time unless they evolve. For companies, it means innovation must continue, because today's lead is not a permanent asset. For investors, it means betting exclusively on technological monopolies becomes riskier. For ordinary people, it means the AI systems, products, and services shaping everyday life may emerge from a broader range of countries than many expected. That's the real significance here. Not one military deployment, not one processor, not one architecture. A shift in how technological power is distributed. There's one final detail worth remembering. The semiconductor industry often looks like a contest between machines. It isn't. At its core, it's a contest between engineering cultures. Groups of people solving difficult problems under different constraints. Nvidia solved one set of problems and built an empire. Chinese engineers studied those solutions and started asking different questions. The answers they're finding may not lead to the same destination, but they are leading somewhere. My prediction is that over the next 5 years, we'll hear less discussion about who possesses the most advanced chip and more discussion about who built the most effective system around that chip. That's where the next phase of competition is heading. And if that prediction proves correct, the deployment we're discussing today won't be remembered as the moment China copied Nvidia. It will be remembered as the moment observers realized copying was never the objective. Learning was. If you enjoyed this analysis, stick around for the next one. The technologies reshaping global power are moving faster than most headlines can keep up with. And somewhere, an engineer is probably reading another export control document and treating it as product feedback.